Okay, first of all, as usual, some announcement quickly, important for you. Yesterday, I did the lab demos for both sessions. You can find the recording for the first one, 10 o'clock, and for the source code that I did for both sessions, I made them available on the website. Feel free to use the source code for your lab. They might be useful. Okay, it's already on the web. And starting from tomorrow, every Friday, we have a TA. He actually took 3311 previously, so he will be very useful for helping you. Okay, so 11 a.m. to 2 p.m. Not my office, 2056. Of course, you're still welcome to drop by my office hour if you like, but it's just additional hours to help you. Okay, so starting from tomorrow, 11 a.m. to 2 p.m. And about part of the requirements for your lab 1, you're supposed to draw a design diagram. I'm making some slides right now to actually help you draw the diagram. They should be ready, hopefully by the end of tomorrow, okay? Over the weekend, the latest. So you have enough time to go over that and apply that to your lab 1 design diagram. Okay. Let's talk about stuff, okay? So last time, we basically went over 5 versions of Java code just to see how you can implement decide-by contracts in Java, right? So the main lesson is you may do it in Java, but it will distract your attention quite easily. So you may want to choose a language that can cleanly shows all the contracts. That's really what I'm trying to do first to give you a rationale why we chose Eiffel for this particular course. Let me just draw your attention very quickly, okay? For preconditions, you actually have to do, from the supplier side, you have to do things if, else, if, else, if, else, if. For different preconditions, you have to throw different exceptions over here. That's what you got to do. On the client side, you are forced to do lots of catch. That's also not good. You don't want to pollute the design, right? For implementation, that's okay. But for design, it's too wordy and too unnecessary. And for the invariants, we actually use assertions, right, on the supplier side. But the drawback for the assertion is it does not appear on the API for the class. Yes? I mean, you cannot hear me, or? My microphone? Did it say that? You mean this microphone here? You're talking about the speaker over here. Oh, that one doesn't affect. That one doesn't affect. Oh, they are independent. Okay, this one I'm sure is working. Don't worry. But can you hear me without the microphone? Okay, how about I don't use the microphone? Okay, yeah. Yeah, don't worry. It's gonna be recorded. Yeah. If it doesn't record, I'll record the lecture again myself and show it to you. If, hopefully not. Hopefully not. Okay, so now, so that's about the catch you have to do from the client side, and also assert for invariants. And now the most exciting part, really, is about postcondition. We briefly talk about a very simple case, but the idea is to write postcondition, you have to somehow save the old version of your attributes or the relevant attributes aside so they can use it manually in the Java version. But in Eiffel, it does it automatically for you. And something I need to talk about in detail about how to interpret the old expressions. I'll talk about it later today. Okay, we'll get there. Okay, just finally, that's about the clean version in Eiffel, right? So you have the supplier account, you got require ensure, and also you got invariants, things like that, right? And also from the client side, from the client side, you simply don't have to do try and catch. That's the idea, okay? So now I want to draw your attention to one thing over here. Whenever you're writing, let's say, precondition over here, or postcondition, everything applies. You normally would like to put a so-called tag over here. So tag is going to be some name separated by underscore and then followed by a colon. So that's actually for if something that goes wrong and you have a contract violation. When Eiffel Studio shows you the contract violation, it shows you the tag. So you know exactly where to locate your error and blame somebody, right? That's what a good design requires, okay, the tag. But for Lab 1, we gave you the tags already. Maybe for your projects later, you want to demonstrate good documentation. You want to put a tag for your contracts, okay? Okay, that's about it. So now I want to move on to this diagram over here. It's really important, and some of you already dropped by my office hour to ask me these questions. How exactly do we check require, ensure, invariance, everything together. Because you got implementation, now you also got contracts. Let's say if the contracts have not been turned off, how does everything work together, right? To really make it precise, I use the simplest example to show you, okay? You have to know what's the timing for to check each contracts, okay? So now let's consider, since we are familiar with the account example, so I'm just going to say over here, let's say we declare ACC to be of type account, let's say. And now we are trying to create a new object over here, and then we are trying to just call withdraw. And so later on, once I finish this particular state diagram, the case can be generalized to any method call you want to make, okay? Let's see the steps, okay? Basically, what I will address is, before we even try to, before the object come to existence, what should be checked? After the object is first being created, what should be checked? And then, after the method is being called, what should be checked? And also before the method. Let me draw a little bit more precisely. Basically, before the creation of the objects, after the creation of the objects, before we try to call a method, and after we try to call a method. So there are 4 things you have to worry about, basically for every scenario for the method call. Okay? But they actually make sense, but I just want to make it precise. Let's just try to go over this particular diagram here, since you guys took 2001. So this one should not be too difficult. I'll just guide you through, okay, to how to read this. So now let's first of all try to find out the starting states for the diagram. So you will agree this is a starting state, right? You just got arrow coming in, so starting states. So what are we trying to do? Basically, whenever you try to say, I want to invoke this particular creation procedure, I want to create a new account, okay? So we are around here, okay? What should we check? If the constructor has a precondition, we should check it. If it does not, we bypass the precondition checks. So first of all, check the precondition for the constructor. So now, there are 2 cases. Either the precondition is violated. For example, you try to initialize with some negative balance, in which case you got precondition violation, right? That's the first contract violation you might see when you try to create the objects. Let's say if everything goes okay, because the user gives you some valid input initial balance to initialize with. And then let's say the precondition for the make is satisfied, then you will now go to a states. I put dotted line, which means the state is not as stable yet. We're not safe, okay? What we should do is, it's not only okay for us to execute the make procedure because the precondition is satisfied, so now we can execute the implementation for this particular routine, right? We try to make the objects, okay? After we have created this particular objects, right? So now we are entering another state. You can think about this is the pre-states, and this is the post-states of the feature call, okay? So now, what should we check in the post-states? Basically, it turns out we're going to check 2 things. First of all, you want to make sure whatever post-condition you might have for the creation procedure, maybe you want to make sure the owner is set to the name, and also the amount is set to exactly A. You cannot just set to any arbitrary balance. Okay? So you're going to check the post condition for that particular constructor. And of course, if the post condition is violated, you got a post condition violation. If not, that's good. You can go to another state. However, it's not that safe yet. What's missing here? Class invariance, exactly. Remember we said invariant is the #1 important constraint on every object. As soon as you first create the objects, you got to make sure not only that post condition for the constructor is satisfied, but also the class invariance. So now over here, we're simply going to check to see if the class invariance is satisfied. Now, if it is not, then you may just get a class invariant violation. So this is the earliest timing you can have a class invariant violation, meaning that after creating the objects, even though the post condition is satisfied, but invariant is not. Okay. After this, let's say class invariant is also fine. So now this green state is really important. Green simply means now we are safe. The object has been successfully created according to the specification of the constructor. and also the invariance is satisfied. So two things. Questions first. So basically, your question was, should we have a precondition for constructor? I would say it depends on what kind of invariance you have. Okay, so you want to make sure if the clients try to create an object, they will call the constructor from the supplier. It would be very important for the clients to pass correct inputs to the supplier so that they can create a valid objects. So that's why we have a precondition. Previously, just make it simple, so I didn't have the precondition. But I think in general, depends on what class invariance you have. Now, in the case of the account class, because we have the invariance, the balance must be strictly larger than 0. So we have to make sure any client passing data to us, they must be able to satisfy the invariant afterwards.
So isn't that the first point of which we account the invariant? That's the precondition. Because it stays the invariant in the concept.
Yeah, you want to make sure the precondition is such that you can prevent any bad inputs from being passed to the supplier. Yeah, and later in the course, maybe towards the end, we're going to see, mathematically speaking, given the invariance, given your implementation, what should be the appropriate precondition to write. There is some mathematical approach or procedure you have to follow, but we'll get there. Okay. Okay, so after this, now look at the green states over here. What does really the green state really mean over here? So this really means now the object is safe. Now you may do anything to it. Well, when I say anything means you can call any method or feature that's defined in the same class. Okay? So now let's say we just call withdraw. Let's say that's the only feature. So now everything will follow a very similar procedure. Let's just try that. So now we are now basically over here, right? I just put green, which means at this moment, the invariance for the object has been satisfied. Now, without looking at the diagram, at this green arrows stage, before we try to call ACC.withdraw A, what should we check first? Should we check invariance again? Because that's been checked already. If you check it again, that'll be redundant. Okay? So the only thing we check before that will be the precondition. Okay? So that's exactly what we're doing. So if you make a request to call the withdraw, first of all, we check to see if the precondition is satisfied. If it is not, we're going to give you a precondition violation. Okay? If it is satisfied, that means we're okay, but it's not exactly safe yet. Okay, we execute the body or the implementation for withdraw. And now, after the withdraw, over here, basically after this, how many things should we check? Two things. What do you mean two things? Post-condition invariant, exactly the same procedure. Okay? Basically, I'll summarize in just a moment. So after this, you can see, after this, first of all, we have to check to see if the post-condition is satisfied. If it is not, then we give post-condition violation. Otherwise, we are okay to actually go back to this particular state where we check the invariance. Okay? Try to go over this state diagram a little bit. I didn't really go 100% detail, but just enough so you can see exactly how things work. Okay? Summary, recap. Before every feature call, including constructor, mutator, or accessor, or query, or command, before every one of them, you have to check to see if the precondition is satisfied in the pre-states. After that particular feature is terminated, you have to check post-condition and then invariance. Okay, that's the summary. And always keep this in mind because when you're trying to design your precondition, post-condition, you ought to know when they will be checked. Right? Is it clear? I hope. Okay. Questions? Yes.
Time that we have like overlapping premises in precondition and post-condition or invariant. Overlapping stuff.
Oh, you mean do we actually repeat the stuff? The question. So I would just say the general design principle is like this, right? So let's say we got a feature F, and then we got require, and also we got ensure. And also at the class level, we also got invariance. Okay, so we got these three parts. Part 1, require. Part 2, ensure. And part 3, the invariance. Okay, 1 and 2 and 3. Okay, so these are the three contracts we might write for the class, right, or for the feature. For number one, which is a precondition, your concern really is valid inputs. Okay, and make sure invariant will not be violated. Okay, that's your concern for number one. And what about for number two? And let me go to number three first. Number three is really about define valid objects. What does it really mean for a counter object to be valid? In which case, the counter value should be larger than 0. What does it really mean for a heap to be valid? That means it must satisfy a certain property, right? That's invariance. And number two, which is the postcondition. So this postcondition is specific to the feature or command or query that you're talking about. I would say we'll talk about postcondition for sure. It's going to be the entire lecture. In general, postcondition is going to make sure the pre-state value for the attributes relate to the post-state for the same attribute in a consistent way. Okay? Basically, the pre-states and also pre-states and post-states values are related properly. Okay, it's a very general guidance. When I say related properly, depending on what you want to do. Okay, we'll see examples very soon.
So even here, the precondition says invariant is not violated. And number 3 is valid object is about invariant.
It's about invariant. Yeah, somehow one.
So are we checking the property of the heap in both of them?
You don't have to. Okay, so in this particular case, yes. You can see over here you can see the precondition over here is the balance, the input balance is strictly larger than 0. You are basically asking this. We also have another invariant which looks basically almost the same. Okay? I would say in general this may not be the case. The precondition has its purpose to make sure the input is valid so that when the supplier try to use the input values, they wouldn't result in invalid states. That's a general principle. But in this simple case, they just happen to be very similar. But I would say we'll see later in cases where the precondition and invariant do not look that similar. Yeah. But we'll get there. Okay, any questions about checking the contracts at runtime? Okay. Okay, I'm going to leave you with this particular diagram over here. Okay, if you got trouble of interpreting that, let me know or rewatch the lecture. But I think this diagram is really important. You want to build that kind of mental model in your mind, okay, how things are checked. Okay, after this, I want to go over just very quickly, just want to show you. So now, when you're trying to do labs or projects, how can you read the stack trace? You know what a stack trace is. Basically, it shows you when something goes wrong, it shows you a stack of the method call or feature call. And the one that actually, the latest one that caused the problem will be the top of the stack, and so on. Okay? So now I'll just show you one example. Let's say we are trying to do, in the client code, let's say bank application. And then we are trying to call the constructor in the account class over here, and we are trying to initialize Alan's balance to be -10. Okay? And because we're trying to call this constructor here, so that means we are calling the make from the supplier, which is account. And then the corresponding precondition here asks us the balance over here, the new balance. In this case, new balance is simply -10. It must be exactly larger than must be strictly larger than 0. Apparently, this is not the case, right? So that means we evaluate to false. Now, you have to know how to interpret whatever message you will see in the eStudio. What you will see in eStudio is something like this. They will show you that the execution simply stops at this point when you are trying to check that particular precondition, right? The new balance, in this case, -10, should be larger than 0. It is not. And if you look a little bit more, you can see that they also show you which precondition exactly that's being violated. So that's why CAC for the contracts is very important when you try to document your contracts. Okay? That's the only one I want to show you. Okay? Maybe you have noticed that already in the eStudio. Okay? Questions? Okay, if you're okay with this, I just, in the notes, I'm going to include that in the iPad notes. They just got different labels, right? It could be this particular precondition with a different label is violated. You can also see that from the stack trace, okay? And also, we got another one for precondition. We also got classic variance violation. You can also get postcondition violation, right? They follow the same manner. Whatever contract that's being violated, if there's a tag, you show the tag in the stack trace. That's the main reason. That's the main lesson here. Okay, so now this is just another diagram, very similar to the previous one. I wouldn't bother you with that. But this one, basically, I just make it more general. Rather than talking about account, rather than talking about make, rather than talking about withdraw, I'm just talking about general invariance or any feature or any precondition, postcondition, etc. Okay? You can look at the diagrams or just generalize things. So that's applied to every scenario you might encounter in the course. Okay? I'll leave that general diagram to you. Okay? It's not that difficult. Okay, so now let's do something a little bit more concrete. Right? I want to start with this where your attention is the most. Right? So now it'll be easier to talk about something more concrete. Let's go back to this example. And this hopefully will help your lab as well. I really hope. Okay. So this is what we talk about at the end of the class on Tuesday, right? As we said, okay, just to remind you, okay, we are trying to just try to specify this particular feature over here. So we say change at, it's going to take some input array. You try to modify at this particular index into a new string. Okay, as you can read from the comments. Okay, for the require, we already said it's very easy. Just make sure the index is valid. You can write 1 less than or equal to I, and also I less than or equal to a.count. That's easy to specify. However, after this example, I would like to talk about the difference between and versus and then. You might be wondering about that too, right? I'll explain that. Okay, but for now, it's okay. Okay, that's a precondition, very easy. Now, what about the postcondition? Okay, to make things clean, I'm just going to wipe out the precondition. Okay, the postcondition that will somehow work together, that we agree, is like this. You can say A, the array, at position I, given that it's valid, that's part of the precondition. After this is exactly equal to ns, right? That's a postcondition number 1 we talk about. This one is okay. Okay. And what we said more right before we finish the class was like this. Let's say if you have the following wrong implementation. Let's say do, okay, and then you simply say, let's say A at position I is assigned to, let's say, ns. Okay, that's the correct implementation. But I do something more. A at position, let's say I minus 1, is assigned to, let's say, ns as well. Or let me make it a little bit more obvious, junk. Okay? Let's say I is big enough so that I minus 1 will give you another valid index as well. You can make that assumption. So now, question for you. Let's say this is the wrong implementation we have from the supplier. The question is the current obligation for the supplier good enough? No. And apparently this is not a good design, because when you try to call this particular feature here, it's actually going to do something more than what you're supposed to do. However, this contract will still be satisfied, right? Because this part alone will satisfy the contract, right? Okay, that's basically what we ended up with on Tuesday. Now the question is, how do we do that? How do we make it complete? Say that again, please.
Every index at the rate that was not I.
Mm-hmm. Okay, that's exactly right. So what you just said was, you want to somehow write a Boolean expression, because now I'll talk about in short. Every index that is not I, the element over there must have the same value as in the pre-states. Is it clear? Verbally, right? Now, let's lead you gradually to the answer. How do we express this mathematically? What should we use?
For all in theory, the universal.
Okay, universal quantification, that's good. Okay, let's try. Okay, we can say for every, let me start with, for every I? For every I? Okay, for those of you who already saw the in-lab demo, you should have some idea about predicate, right? Such that, let's say, I should be from 1 less than or equal to I, less than or equal to a.count, let's say. Okay, this is the range, and we want to put some constraint over here. Now, what should we put? We want to say something like, if the I, oh, you know what, I shouldn't put I. That would be a little bit confusing to you because we got I already. If you don't mind, I'm going to change this to J, okay, just to avoid confusion. Okay, we'll talk about 2 different dummy variables. Basically, I want to say, I'm going to consider all the indices for this particular array. However, I should only be concerned about those J's that are not I, because I has been already handled by the first postcondition, right? So we're doing separation of concern. So now, how am I supposed to write this guy here? Okay, sure. Let me start with that. You can help me out. J is not equal to I, then? Okay, let me write, okay, I heard different things. Okay, let's say OAJ somehow is the same as AJ. If I only write these 2 separately, it's not a Boolean, is it? Right? So now the question is, should we write AND or implies? That's the question. Somehow we want to combine these 2 Boolean expressions using logical operators, right? But we only got 2 binary operators to choose from. Oh, we got 3, either AND or implies. So now we got, so what should we put over here, right? It's a placeholder. Should we put AND, should we put or should we put implies? Okay, how about, I tell you what the answer is, we should use implies. That's the answer. However, you don't memorize it. That's not my style, right? You should really understand the reasoning behind. I will leave the explanation for or to you as an exercise. But let's explain the AND case. Okay? AND should not be the way to go. Let's use a concrete example to explain. Okay? Let's say this is your array. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay? The contents doesn't really matter. Okay? Let's say we got 5 indices, index 1 until index 5. And let's say the I we are talking about is simply just 3, which means we are trying to modify basically this particular index over here, right? That's the intention. Everything else should remain the same. Okay? So now let's say we actually put AND over here. We say for every j that's in between for every j that's in between 1 and a.count, j must be not equal to I, and also the old value must be the same as new value. That's basically what we are trying to say. Okay? Can anybody already see this postcondition in this particular scenario will fail right away in the first iteration? Can anybody see?
There will be a case where j equals I and the holding value is false because there is universal.
Okay. So now let's try. Okay. So now let's try to trace a little bit over here. So we'll keep the case for n over here. So now we know that j, the value for j will be 1, 2, 3, 4, and 5 conceptually, right? So now a question for you. Over here, let's say we are talking about the correct implementation. Okay. So what we're trying to do over here is for the first iteration, j will just be index 1. Agree? In that case, we'll simply just do j, which is 1. 1 is not equal to I, which is 3. Is that true or false? That's true, right? Okay, so that's true. Okay, let's only worry about left conjunct. Okay, and then for the second iteration, j will be incremented to 2. Okay, not equal to I. This will also give us true. Now here comes the critical points. Go to the third iteration. J will be incremented to 3. 3 is not equal to 3 will be false. And because this is conjunction, false give us false. Doesn't matter what the right-hand side is. That's why conjunction is not the way to go. Your very intention for writing this is because when I reach the index that is equal to I want to ignore it. That is why. So now, basically, logically speaking, is there any operator such that f that operator, whatever, is going to give me true? Implies, exactly, right? Because you know that false implies anything will just give you true, right? That's why we got to use implies. Don't be too surprised if later in the exam, maybe not in the lab test, that might be a little bit too harsh. In the exam, if I simply give you a contract where I was supposed to use implies, I actually use and. You got to explain to me why that's not an appropriate postcondition. We do have some exercises for you, okay? But we'll practice that. But think about this issue here. Okay, so what we should really do is we should really put, rather than and, we should put implies over here. That's the correct answer. Okay? This pattern is so useful. You're trying to go over some collection. It may be a linear array, linear linked list, or even a tree. Okay? You want to say there are certain cases I don't care. You can just get by. But there are some cases I do care, in which case the premise of the implication should just be true. Okay, that's the answer. Okay, let me write it more cleanly, and then let's see how we can turn that into Eiffel. Okay, so now what we eventually get, mathematically speaking, what we get for every I such that 1 less than equal to I less than or equal to j. J, and then a dot count. It is the case I is not equal to j implies that aj is the same as old aj, the old value. However, let me just warn you a little bit. The way I write the old expression over here, after the whole lecture, you might realize it may not be exactly what you want. But I'll save that a little bit. That will add too much complication at this point. Okay, just conceptually, it's the old value. Okay, it must be the same. Okay, so now how do we translate this into Eiffel? Let's do the translation, and then finally, I want to show you in a small example why this postcondition work. I think that will be complete. Okay, let's say that's the postcondition. Given what you attended yesterday, you should be able to translate this. Okay, what should I do? Across. Okay, across what? 1. Thank you. Okay, vertical bar dot dot, and then a dot count. Very good. Okay, and then, so now you have the option, either is or s, right? Let's say use is, okay? So you don't have to refer to the cursor of the item. Is, let's say j, but you're more advised to maybe put L underscore prefix just to avoid clashes, okay? What do you mean, what class? Oh, the clash. No, not class, clash. Yeah. What clash? So let's say if you already have a local variable that's already called j, in which case you cannot do it. Oh, what I meant by is this. Let me make it precise. Let's say this is what you have. You got feature f, you have local variable over here. Let's say j. Okay, you got I here, and then j is simply just integer. And now you have your ensure. And then you have your across something, and then you say is, and now if you put I or you put j, it's going to clash. Okay, that's what I meant. Okay. You can think about it belong to the same scope. Basically, local actually applies to it applies to the feature itself. And also, this I and j, they should make sure you do not clash with the feature. Yeah. Okay. So I should not clash with I here, and j should not clash with j over here. Okay. Both are not good. So better choose another name. Okay. You might run into this error when you do your lab 1. Okay. Just be careful. Okay. So now let me go back to this. Okay. Let's say I choose L underscore j. And now should I do, I should do all, right? You all know. Okay, so now I can say I not equal to Lj implies. Actually, when I put in math, I should have put this, right? I should have, but I just forgot. Implies Aj tilde old Aj. Okay, that's the postcondition. It's almost perfect, except the use of old, but we're going to see that. Okay. A final thing to mention, just to make everything complete. Okay. A final thing to say. Let me start a new one. For every, let me just repeat it. Bear with me. So j such that 1 less than or equal to j less than or equal to a dot count. It is the case a. So now let me combine both postconditions together. What do I mean? You can see we have postcondition number 2 over here, which means we have to make sure in the case of I not equal to j, we don't care, right? Oh, sorry, in the case of I equal to j, I don't care. That's what I meant, okay? So this is going to handle the case where I is not equal to j, and we have another one which is going to handle this, right? Is it possible to have a single Boolean expression that's going to combine these two cases together? And, okay, basically you somehow want to use implies and for all everything together, right? Okay, good. Let's use this as a final version. So now it is the case, right? So now it should be a big conjunction, right? Case analysis, basically. I equals j implies Aj is simply assigned to the new string. New string. I is not equal to j. That means doesn't change. Aj is the same as old Aj. That's the final version. Logically speaking, is everybody comfortable? Okay, you can see overall it's still a Boolean condition. The final thing I would like to do, as a practice for you, try to put this into a cross. Okay, you just have to play with the conjunction a little bit. Okay, that'll be exercise for you. I think that for those of you who are still a little bit lost as to why this postcondition works at the runtime, let's do one example very easily. To make it very easy, I will just talk about an array of size 2. A is simply pointing to this array, and let's say we have index 1, index 2. Let's say we got Alan over here, and also we got Mark over here. That's the input. And then we are trying to call change at. Okay, I want to change at position 1. And then, oh, let me just be precise. I want to change at array A, change at position 1. I want to change from Alan to Tom. Are we good? Let's say. That's what we are trying to do. And let's say we have a wrong implementation. The wrong implementation is actually going to do A at position I, well, let's say I, is going to be whatever the new string is. And also it's going to do I plus 1, try something a little bit different. It's assigned to NS as well. Let's say that's a wrong implementation. According to the wrong implementation, what we will get after this, let me, just easy for comparison, right? Let's say this is A. Let's say A, let me say this. This is the new version. So now how should this look like after this? Tom, Tom. Tom, Tom. Okay, notice that this is the old version, right? That's what the implementation will do. So now let's try to run this predicate together, okay? So now if you run it, so now for the very first iteration, okay, for the very first iteration, I would just be, sorry, not I, J. For the very first one, J, A dot count would just be 2 in this case, so 2 iterations. Now J would just be 1 to start with. Agree? So now we know that I is always just 1. I is just 1. What's J in this case? 1. So 1, 1, and 1, 1. question for you. Is there a conjunct I know the result already? This guy here, right? Because 1 not equal to 1 is already false. So for the first iteration, I know that this guy here is already true. However, I still have to see whether this guy here is true or false, right? I don't know the result yet, okay? So now 1 is equal to 1, and then AJ is NS. What's NS? It's Tom. Is A1 Tom? It is. Okay, check for the first one. That's the first iteration. Second iteration. For the second iteration, let me use pink, okay? Hopefully you can see the difference, okay? For the second iteration, J will just be 2. So now, I remains to be 1, but now J is 2. J is 2. Is there a conjunct that's trivially true? The first one, exactly. You can see 1 equals 2 will just give us false. Right? In the first iteration, the second conjunct is trivially true, but for the second one, it's reverse, right? Because we're talking about different cases. So now this is simply just false, so we don't have to worry about this. Okay? And now, what we have over here is 1 not equal to 2. True, right? So now we have to check this. Basically, we're comparing A2 and A2, the old version and the new version. Are they the same? They are not the same. So that's why we're going to get false in the second one. So overall, it's going to be a post-condition violation because the whole predicate reevaluate to false. Is this a good thing? Oh, yeah, that's true. You're talking about supply. Supply is really bad. But the fact that we have violated post-condition when the supply is bad, is it a good thing? It is a good thing. It's a good design. Okay? Any part that's not clear, please. Yes?
For the first part.
You mean the first conjunct?
Yeah.
Yeah.
The first one.
Mm-hmm.
Is the first part where you ensure that I and J are the same, is that necessary?
It is necessary because remember we are actually having just a single post condition for this particular change at. There are two cases. Either it's the index you're trying to change, you intend to change, or second case, it's an index you do not intend to change. That's why I split that into two cases. That is why. Right? Yeah. Okay, guys, let me just highlight very quickly, and then please study that. Get to me if you need some help. Again, this is a very common pattern for case analysis, right? Using these operators all together. Okay? Yeah. Good.
My task would be to put into Eiffel code whereby well, I can see how to do it differently.
Mm-hmm.
What would you want the ideal solution to be?
Oh, I would say, yeah, this is pretty good. Yeah, it's a single post condition where you can use across, implies, not equal to, everything together. So take this as an exercise to turn this into Eiffel. It should be very straightforward, but it's a good practice for getting familiar with the syntax. Yeah.
So these two statements, if I translate them to Eiffel, would actually be one statement instead of like two?
It will be one single across.
Okay.
Yeah, okay, so let me write it down for you. Oh no, not the answer, right on the question itself. Okay, I think it's better for you to practice. So practice, please. Turn this into a single across. Just a single one, okay?
Just want to segue this on post conditions to tags and the power of tags. In the sense that, is there any bound or like, so I know tags are used to identify some type of Boolean expression, but that's one line. Can we have multiple lines of Boolean expressions? Let's say.
Yes, you may. The question was, is there a maximum number about how many post conditions you may have? The answer is no. Let me illustrate. And precondition invariant apply the same way. Let me just say post condition. Feature F, you have require something, and then you have ensure over here. Let's say I have tag number 1, colon, and then I have post condition number 1. Okay? Tag number 2, colon, post condition number 2. All the way to tag n, right? I have n, colon, post condition n. So now I got n post conditions. Okay? n can be as large or as small as you wish. The minimum will be 1. The maximum will be whatever you need, right? So now, this guy here is completely equivalent to, if I just have a tag over here, I simply say P1 and P2 and all the way to Pn. So a new line in your postcondition simply means conjunction. So you will see, for example, in your lab 1, where I ask you to do for a precondition, I may have asked you to do maybe 2 preconditions. That means doing this and this, right?
Sorry, so I understand what you said, but what I'm saying is like for one given tag, the next line, the next follow and after tag should be some expression, right? Now,
Correct.
If you don't follow that line, the second line, that which is expression by another tag and instead follow up another expression, is that valid? That's what I'm asking.
You're trying to ask the following, okay? So the text over here is actually optional. Let's say you have the following. You got F feature, and then let's say we have ensure. Let me say I have tag 1, and then I simply say X strictly larger than Y. Okay, just for example, okay? After this, I have another one to say Y strictly larger than Z. Okay, so now that's your question basically, right? So now, how many postconditions do we have in this case? Or it doesn't compile. Actually, we got 2 postconditions over here. Okay? The first one has a tag. The second one does not have a tag. That's the difference. That's the first postcondition with a tag, which means if you violate that particular one, it's going to show you the tag in the stack trace. The second postcondition does not have a tag, which means if you violate that, it's only going to show you the expression itself rather than the informative tag. That's the only difference. Okay. Yeah, of course. If you try the following, as soon as I try to say, okay, let me just for completeness. In short, let's say T1 over here, X larger than Y. Compare these 2 versions. Y larger than Z. What if I put N over here? Now, how many postconditions I have? Even though I have 2 lines, doesn't matter, right? Because I got an N over there, right? N is going to, the compiler doesn't worry about the spaces or new lines, okay? Okay, so now in this case, we have a single postcondition, right? Just that. Just a single one. Yeah? I would say it's a good practice. The good practice is each pre-postcondition or invariant should have its own tag. Yeah, otherwise it can sometimes be confusing, right? If some has tag and some does not have tag. That's why when I show you the lab 1, all the precondition, postcondition invariant have a tag. Yeah. Yes? Can you iterate through the array itself? Yes, if you refer to the in-lab demo yesterday, so the more general solution is to go across from the lower bound to the upper bound and use that as the index. That's the most general solution. But in some cases, you may just want to check for every element in the collection or the array. That's also fine.
Similar to like the for I and versus for each loop?
Yeah, exactly, yeah. So I would say, no, actually, in this case, it does make a difference. Tell me something. For this particular example, is it possible to get by without mentioning the indices? Right, because in this case, you do need an index. Actually, that's a perfect example. Let's say this. Let's say you have an array of strings, of names. If I simply want to check if all the strings are non-empty string. In this case, indices or position does not really matter. In which case, you can say across the names as n. And then you simply say n is not empty. But in this case, the position does matter. Actually, I like that question. Yeah. Guys, do you know what I'm trying to say here? No? No worries. I'll repeat. No worries. Let's say over here. Let's say I have an array over here. NS array of string. Simply names. So now, how do you express the following Boolean expression? Are all the names in NS non-empty? That's the question. Okay? So now, are the positions really important in order to write this Boolean expression? Positions. Well, when I check for each element in the names, does it really matter whether this name is in position 1 or in position 5? Well, it only matters whether it's an empty string or not. Should be the latter, right? So this is the simpler one to write. I'm going to write both versions for you, okay, in across. Okay? That will actually illustrate more concretely. Okay? Version number 1, you can always use indices. You can always use that. Okay? You can say across, let's say 1 until, I shouldn't say until, otherwise you get confused. 1 up to ns.count. S, let's say we don't have any clash, I would say I. And then I would say all. ns at position I dot is empty is not the case. So I can say not. That's version number 1. Does it make sense to everybody? Okay? You can always use the indices option to specify if that can be if that's expressible. Right? However, in this case, the positions in the array does not really matter. All that matters is whether the element itself is empty or not. So what we can do instead is to write another version. Okay, version number 2. Across ns. Okay, so now let's say, oh, what? I made a small mistake. I'm not sure if you noticed that. I wouldn't blame you. Ah, very good. Thank you. Right? What if I keep s? What should I do? IDA. Oh, you guys are very good. I hope you'll be the same good in the lab test, right? Yeah. Please, right? It's okay if you stay quiet, in the class, but better do it right in the lab test, right? Okay. Huh? Oh, okay. You didn't hear. Okay, no worries. Okay. Basically, the point is, if I write s over here, it's going to be a compile time error because s means I is a cursor rather than value, right? I gotta say I the item over here. Okay, so we better keep that just is. Okay, yeah. Review the in-lab demo yesterday. Okay. I don't care whether you use across s or across is. Doesn't matter. I have no problem with either one, but you better get it right. Okay, that's what I care. Okay. Okay, so now I can say is n over here. Now, what would be the type for n? A string, right? Just a member, since I'm using is. And then all I can say ns dot is empty is not the case. It's not empty. Which one? Oh, yeah. Absolutely. You guys are very, very good. Any question about this? Okay. Oh, no, actually, in this case, oh, you mean for empty? Or what if we got empty array? Oh, good question. Good question. Guys, let me ask you this. For this particular example here, that's something I want to say a little bit later anyway, right? So it's better to say it now. Question for you. So now let's say this. If this is the array I'm talking about, let's say this is the array, ns, okay? Let's say ns is simply a and b and c. So this should give me true, agree? Every string is not empty, right? On the other hand, if I only got, oh, sorry, well, I meant to wipe it out. If I got this, that should be false, right? Because at least one of them is not empty. At least one of them is empty. Now, question for you, okay? And this does require a little bit logic, which you like, right? Let's say ns is pointing to an empty array. It does exist, but it just has no contents in it. So ns.count will just be 0. What would be the result, first of all? True or false? I heard true, that's good, but why? It wouldn't go to loop, that's exactly right. However, well, logically speaking, what does that really mean?
What if there was a true and then there's a conjunction here? Like a true, like the first one was a conjunction, and so then if you didn't have it, then it would just...
You're getting somewhere, not quite. You're getting somewhere. Okay, one more, how about that? Okay, yes. Exactly right. That's because if the collection is simply just empty, you cannot find any counterexample to contradict this property. So the property must be true. And what I'm really trying to say is exactly this. And please review this particular property. For every x, Rx, false, that means empty range. I'm pretty sure you learned that in 1090, right? I'm pretty sure. I'm just trying to review. This will always give me true, because the range part can never be satisfied, so you can never check anything. So you can never find any violation for the property. So the property must be true. Okay, that's what you learned in 1090. On the other hand, you have a counterpart. There exists x, and the range is simply just false. And then you have some property px. What would this be? False, you all know very well, but what would be the intuition behind? You have to find one witness that will satisfy the property, but you cannot. Exactly right. Yeah. Okay, I'm just trying to show you, logic does correspond to runtime sometimes, right? It's just not random. Okay. Again, back to the original concern. If you write across like this, if you simply just got empty array, it will just give you true. Okay, and that's right, because you cannot find any string that's not that's actually empty in the array. So that gotta be true. That's questions. Are we okay? Good. All right. Okay, after this, what I will do is, okay, so now I will do the short circuit maybe next week. I do want to go into about object copies. I think that may be a little bit more worth talking about it right now. Okay, I'll come back to this. Okay. Okay, let's talk about copying objects. We definitely cannot finish everything, but at least I can start. Okay, we got some time. Questions? Yeah.
Something about O keyword you mentioned.
O keyword. Yes, we'll get there. We'll get to O keyword. We'll definitely get there. Okay, so now I have a question for you. Back in 2011, did you actually have to implement things like a shallow copy, deep copy kind of stuff? No, okay. So that's worth mentioning, the concept, okay? Because the whole lecture over here, you can see the main idea is really about how you can write complete postcondition. But in order for you to write complete postcondition, you need to have a very good sense about what does the O keyword really mean when you write it. And number two, what does it really mean when you want to do a shallow copy, or you want to do a reference copy, or you want to do a deep copy? Okay, it's going to make a difference when you write a postcondition. That's why I want to mention this. Okay, so what we will start with is I'm going to have some idea, give you some idea about making copies of objects, reference versus shallow versus deep. Okay, and then we'll do some example, and then we'll go to O expression. Okay, that's the idea. I think that the latest timing will be to finish this lecture hopefully on Tuesday. So you're completely ready. Okay, I don't think lab 1 will require so much of the knowledge of here. So you're fine, but you got to learn it. You need that for lab 2. Okay, so let's talk about how you can copy objects. Okay. 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 So what I meant to do is I want to. Is this the one? That doesn't seem to me. Okay, give me one moment. Okay, sorry, I want to switch the lecture. Here, copying objects. That's what I meant to do. Okay, so now how do we copy objects? Okay, so now let's do some illustration. Okay, so what I would do is let's now make the following assumption. Okay, I just want to visualize it. Okay, let's say right now we have 2 objects of type C. You can see that is why we got C. I'll illustrate to you. Okay. So we have one object, we have another object. Both of them are of type C over here. And you have attribute A only. And C1 is pointing to there. C1 stores the address of the objects. And C2 also stores the address of that. Okay, so far so good? And the attributes for each one of them simply just point to something. Might point to other complicated objects. Okay, that's the scenario we're going to use to illustrate reference copy versus shallow copy versus deep copy. Okay, that's the example we're going to use. First of all, any question about this diagram here, first of all? Otherwise, you're going to get lost for the next 10 or 15 minutes. Are we okay? Yeah. Okay. Basically, assuming that we got a class called C, we just got one class called C. And we have two instances of this particular class. In class C, we got an attribute A. A might just be another reference type, which will point to some arbitrarily complicated objects. Okay, that's why I say C1.A is referring to this particular structure over here, right? And C2.A is just referring to another object structure. Okay, is that okay? Yeah. Okay. No doubts about this diagram here? You need it. Okay, that's the simplest way I can think of to illustrate. Okay, so now let's talk about what does it really mean to make a reference copy. Reference copy is very easy. Basically, let's say if we have over here C1 is assigned to C2 only, what does that really mean? Well, back in 2030, I'm pretty sure I emphasized to you guys, right? You're trying to copy the address of C2 into C1. Diagrammatically, how do you change it? Should I change C1 or change C2, the arrow? C1 or C2? C1, right? Because you're trying to assign to C1, so C1 must be changed. So C1, rather than pointing to here, is now going to point to here. Reference copy is the easiest. Okay, just that. That's how you have aliasing, right? That's reference copy. That's it. Okay. Shallow copy is a little bit, you're trying to do a little bit more work. Shallow copy. And in order to do shallow copy, you would say C1 is assigned to, now C2 dot twin. That's, I forgot what the corresponding thing in Java is called, but it's in Eiffel just called twin. You're trying to make a shallow copy. And what does shallow copy really mean? Shallow copy also has another name. It's called the first level copy. Okay. Eventually, we're going to modify the pointer over here. Eventually. Let's not do that just yet. In order to prepare C2.twin, what should we do? Okay. In the case of the reference copy, we don't create any new objects. But now in the case of shallow copy, we have to, at the first level only. So now we know that C2, we're going to make a twin of that. We're going to make something like this. Create an object of type C, which has the attribute A. And we are done with the first level already. No more complicated copy anymore. What about the attributes over here? Should we make a duplicate of the cloud? We shouldn't go further. Okay? What we do is copy the address of the cloud. Okay? Copy address of C2.A. Diagrammatically, I will just let this point to the same cloud. The orange object I just draw is the twin, shallow copy of C2. And then, when I try to do this particular assignment, I'm going to change C1 so that C1 now points to this particular new object. Let me just explain a little bit more before I answer your question. Okay, let's do a little bit check to emphasize your understanding. Let me go to the previous one here. Question for you. After the reference copy, if I say C1 equals C2, and equals means comparison, right? Would that be true or false? True, same object. Thank you. And what about C1.A equals C2.A? Would that be true trivially? It would be trivial, right? Because C1 and C2, they simply point to the same objects. So when you say C1.A and C2.A, they simply point to the same cloud. So it's trivial. They are just the same. Okay? Okay so far? Good. True and true. Now, let's go to the shallow copy here. Now, if after the shallow copy, if I do C1 equals C2, true or false? False. That's because of the first level copy, we create a new object to begin with. So that'll be false. And now, if I say C1.A equals C2.A, it's true. They refer to the same cloud. Okay? Hopefully that emphasized it, reinforce your understanding a little bit. And you have a question.
Yeah, so my question was,
Yeah.
with this kind of copy, if I tried to edit the C1.a, would it end up editing C2.a?
It's a very good question. Very good question. The question, I forgot your name. Shadi. What Shadi was asking was, let's say we do the following, right? After this particular assignments, it's a very good question. After this, I simply try the following. If I say C1.a dot, let's say set some value. I'm trying to change that object here, which means I'm trying to do a little bit of stuff over here. Okay? The question was, now after this, if I try to look at C2.a, will C2.a actually show me the same change, or will be unchanged? Same change, simply because they refer to the same objects, right? Because they refer to the same cloud. It's a good question. And by the way, it's called aliasing, right? Right. Aliasing simply means multiple variables store the same address for the same objects, right? Okay.
Is that what you said, the word that is, corresponds to twin in Eiffel, like alias?
No, actually, aliasing is a very general term that applies to Java as well. Yeah, I think for the folks who I taught 1022 and 2030, I kept saying aliasing. But if you forget, that's fine. Oh, you're excused. Okay. Yes? Good question. I always got this question. I like it, right? So that's why I don't even bother mentioning. I know I will be asked, right? Good. So now the question was, let's say after C1 is assigned to C2.twin, so that means this pointer is gone. So now what happened to this poor guy here, right? I would say it depends. If there are other pointers pointing to this particular object, that means somebody else still depend on this object, it will remain there. It's just that whenever you talk about C1, you are not talking about this object anymore. Okay? However, you just lose track. Okay? Second case, if there is no other pointer pointing to this particular object, it will be garbage collected automatically. If you program in Eiffel, C# or Java, things like that. However, if you program in C back in 2031, you have to do free. Yes, yeah, exactly. Yeah, that's a word. Exactly, that's right. Okay, that's about shallow copy. I would say shallow copy is actually the trickiest one, because deep copy we're going to talk about goes to another extreme. Okay, deep copy. If I want to do deep copy here, so I would say C1 is now assigned to C2 dot deep twin. Okay, you just got to remember the word. Okay, deep underscore twin. You're going to do a deep copy, and the principle is so easy. You just completely duplicate the objects recursively. Okay, the main thing is about C2.a over here in general can be arbitrarily complicated. Maybe it's going to refer to another object, which also refer to another object, and also refer to another object, and also point back, something like that. Right? It can be arbitrarily complicated. The deep twin somehow is going to make sure everything is copied to is going to be duplicated separately, completely. Deep copy. Okay? But you don't have to worry about how to implement that. All you got to know is it's going to duplicate something completely. Yeah.
So in terms of deep copy, if you change like C1 that's
Oh, yeah, we'll get there. Yeah, you're basically asking whether aliasing should be in effect anymore. The short answer is aliasing should no longer be there. And let me give you a little bit heads up. We talk about the three copies, and then we're going to do a little bit example to illustrate even more. And the lesson is to really make sure your contracts can completely block any evil supplier. You very often have to use deep copy, deep twin. And the next concern will be, oh, wouldn't that be inefficient? True, you got to duplicate all the object structure. But remember what we said, the contracts are not meant to be efficient. They're meant to guide your developments. As long as the contract really serves the purpose of guiding your design to be the valid one eventually, you can turn them off anyway. Okay? But now, okay, we're going to explain deep copy, and you got a question. No, not yet. We haven't even talked about deep copy yet, right? And all keyword will come a little bit later. Okay. Okay, so that's okay, deep copy. Okay. So now, how do we actually, in this case, how do we implement deep twin over here? Basically, the first step will just be like a shallow copy. You create a new object over here of the same type, C, and then attribute A. So now, question. In the previous case, we simply make a new pointer over here to make the shallow copy. Now, what should we do? You can make a completely new cloud, complete duplicate, right? It's going to point to something that looks just like C2.A, just like that. Okay, so I would say duplicates of C2.A, okay, complete duplicate. And notice that this cloud and this cloud do not overlap whatsoever. That means there's no aliasing going on, right? And then, how do we do this assignment here? So C1, rather than pointing to here, is going to point to here. And let's now do another check. Remember, we always do whether C1 equals C2 and also C1.A, C2.A. Let's do the same thing, okay? So now, what if I say C1 equals C2? False, right? The same as the shallow copy, just the same. But now it's going to make a difference. C1.A equals C2.A? False as well, because it's completely separate. Okay, that's the 3 copies. Okay, conceptually, right? Yes? Oh, you mean the equals, right? Okay, I would say the question was, I'll just address that very briefly. Okay, we don't have to worry that for this stage. The question was, what if I simply do the tilde over here rather than equals? Okay, first of all, let's understand what's the difference between tilde and equals. Equals simply means like an equal in Java. You're trying to compare addresses. But for tilde, it's like an equals method in Java. In Java, what would be the behavior for the equals method? By default, it's just like equals by default, if you do not override the equals method. But let's say if you have already overridden the equals method, it will compare the contents. Okay? So I would say the tilde over here will add some unnecessary complication at this level, so you don't have to worry. Okay? But just know that when we talk about equals here, it's just comparing addresses just for now. Okay? But later on, you might realize you may have to use tilde sometimes. Okay? Yes? How do you, oh, tilde. Oh, yeah, that's something I didn't ask you to do in lab 1. I thought might be a little bit too much. So maybe in lab 2. In lab 2, you have to somehow try to see how you can override or redefine. That's how the term we use. How you can redefine the so-called is equal feature in Eiffel. That's something we'll get into. That's exactly the point. You try to specify how 2 objects of the same class are supposed to be compared. You'll see that. Yeah. Guys, any question about the 3 kinds of copies? Okay. And then we got 10 minutes. I don't think I can get to the old expression today. However, we can set it up so that when you come on Tuesday, you'll be completely ready. Okay. Let's now go a little bit further. Okay. Before that, if you try to read OSC2, okay, if you try to, okay, I will tell you, okay, everything has been said, okay. What I want to quote to you is, oh, I forgot the page number. Anyway, so if you read about the corresponding chapter in the textbook, they have this diagram over here, okay. I'm just trying to help you how to understand it, okay. That's a little bit complicated, I would say, okay. So what I will try to do is like this, okay. So now what I'll try to use a highlighter to highlight for you, okay? Let's say in the beginning, we have let me just make it a little bit, okay. Look at the blue. This is the initial setup. It's pointing to this particular object over here, which is one of the attributes pointing to itself. And also it's pointing to another object over here. And that's kind of the object structure we have over here. Okay, I'm just trying to redraw over here. Okay, first of all you got to know is the blue one is how you start with. And we're going to see what will be the consequence of doing reference copy, shallow copy, and deep copy. That's what we're going to see. Okay, the easiest one is by doing a reference copy. Okay, what does it really mean to do a reference copy when I say B is assigned to A? Do I make any new objects? No. I simply copy the address of A into B. So now B is simply just going to point to wherever A is pointing to, just the same pointer. Okay, that's a reference copy. Okay. What about twin? Twin, as we said, is also called first level copy, pink. So now if I say C is assigned to A dot twin, first of all, we have to create the same object type as this. Okay, it doesn't really show the class name. It just show the name, but that's okay. We just basically copy the same, just do a first level copy over here. Okay, so we are doing this. Okay, just a new object. However, just show you one link. You can see for this particular attributes is referring to this object over here, right? That is why for this attribute over here, it's going to refer to the same object over here, just a reference copy at the second level. Does it make sense? Okay, I'll just go until there. Okay, and finally, I think that this particular link might be the most difficult to decipher from the textbook. Okay, I would say it's a poor representation. But one final thing. What about deep copy? If I try to do maybe deep copy over here, if I say D is assigned to A dot deep twin, that simply means not only that I'm going to create a separate object over here, but also everything else is just going to be duplicated recursively, right? So you can see this is completely separate from the original object structure, completely separate, no aliasing. Yes?
But why do you get bigger of it? You take a bigger of?
Which one? You mean the 06? Are you talking about 06 over here? 06 is simply just a deep copy of this 02, basically.
So why is it deep copy? Because wouldn't this take the deep copy of the name language one?
No, it was simply thinking this way. So basically, let's see. Let me follow the link properly. Okay. Okay, like this. You can see the original object is over here, and then this particular attribute is pointing to this object over here, and then that object is also pointing to this particular object, right? That's kind of the link. So just follow that kind of structure, right? So as I said, implementing this will be a very nice exercise. Maybe I can convert that into a lab. Next year, don't worry. Next year, not this year. Yeah. Next year. And the right contrast for that will be extremely fun. Okay, anyway, you don't have to worry about it. Make sure you don't take it with me again, right? You're welcome to. I'll be very happy to see you again. Yes, question, yes.
For C,
Yeah.
why does the plan work for that point all the way up to the original one?
Oh, okay, let me, you mean you're asking about this? Okay. Okay, let me just make sure I'm answering the right question. You're asking for this particular shallow copy over here. Why do we have this particular link? Okay, no problem. Okay, remember we are trying to do a shallow copy, right? Shallow copy means we only trying to create a new object at the first level. And then over here, after the first level, we simply do some reference copy just for saving the reference, saving the space. So now you can see for this particular attributes, it simply just point to this particular object, right? So this will make sure it points to just that the same object as well. That's why, yeah. Okay, we're good. We got about 3 or 4 minutes. I'll do as much as I can, right? Okay, so now it might be nice to just go over one or two. Okay, so now what we will do is, before I even talk about old expression, I would like to just give you another slightly more complicated example where we're going to simulate old version and new version of array. You can imagine that the new version of the array is going to be in the post states. The old version of the array is going to be the pre-states somehow, right? But don't worry too much about the pre and post state just yet. Focus on the example, okay? But I give some special name just to be more informative. What we're going to consider is, basically this is just a reminder. Every time if you have a reference type, that simply means store address only, okay? Okay, now let's look at this. Let's assume we have two local variables, imp and old imp. Imp is the new version. Old imp is the old version. That's why I chose the name. Okay? They are both array of string. And we're actually going to try to do the following. We're trying to make, I'm going to show you a diagram first, and then I'll say that. And then we simply create an empty array for the imp. Okay? And then also we're just trying to force the Alan, Mark, and Tom. Just 3 elements array. Very easy. Okay? So what you will get is something like this. First of all, let's convince this diagram makes sense. You can see that imp is pointing to an array of size 3. Imp at position 1 is pointing to Alan. Imp at position 2 is pointing to Mark. Position 3 is pointing to Tom. And for the old imp, not initialized just yet. Okay? That's a setup. Okay? So now, basically what we're going to do is to see how can we initialize the old imp in the 3 different ways. Maybe the old imp will simply just be a reference copy of imp. Maybe the old imp will just be a shallow copy of the imp. Maybe the old imp will just be a deep copy of the imp. Let's say we made that particular copy already. After we have done the copy, if we try to do something to change imp, is it going to affect the old imp? Depends on the copy, right? Guys, you know what I'm trying to do? I'm trying to mention the roadmap to you. Let me repeat in case you don't quite follow. We're going to initialize the old imp in 3 different ways. Either a reference copy of imp, shallow copy of imp, or deep copy of imp. And then we're going to do some kind of changes to imp. And then after the particular change, we want to know whether that change will be reflected to the old imp. That's what we want to know. Okay? You want to take a guess? Okay, you first, yeah.
Reference would change it, and shallow would change it, but deep wouldn't, because deep is entirely.
Is entirely decoupled, right? Okay, Jordan, anything to add?
Same thing.
Same thing, okay.
Would ensure that the values in
Okay.
the old values.
Okay, it seems like for reference copy, you pretty much know it's going to reflect that because you're referring to the same copy. And for the deep copy, of course, it's not going to affect. It's completely set. What about shallow copy? That's kind of a like gray area, right? Yeah, so I would say for the shallow copy, it depends. Again, it depends, right? I'll get there, yes.
Since here we're talking about strings and they're not like very complicated objects. And
Oh, actually, string, it's more complicated than an integer. If you think about integers like a primitive type, string is like an object type. So I think it's just more complicated enough that we can illustrate. Okay, how about just up to here? And then remember tomorrow, between 11 a.m. to 2 p.m., you got TA hours. Okay, I'll see you next week.